We're going to go over this warm up before we get started in the main part of class. So on each of these, you can use your Desmos graphing calculator if you need it. If not, that's just fine too. 2 to the third power, that is 8. 2 times 2 is 4, times 2 is 8. 5 to the third power, well, 5 times 5 is 25, times another 5 is 125. 1/2 to the third power, well, I can think of that as 1 to the third power over 2 to the third power, which is 1 over 8. That's also, if you want to convert it to a decimal, 0.125. 1 to the 1,234th power. Whoa, that must be a really big number. To the 1,234th power. No, it's just 1. Good morning, Callan. Glad you're here. 17.5 to the 0 power. That seems confusing, but it's not. Anything to the 0 power is 1. All right. Any questions on those exponential expressions? When it comes to these other ones, it's kind of helpful to think about what this says in terms of exponentials, because I I don't have my logarithms memorized really. So think of this as equal to some variable x. And then we can convert that to exponential form. Because that's log base 2 of 8 equals x, it's base 2 to the x power is equal to 8. So what that says is 2 to what power equals 8? Well, 2 times 2 times 2 is 8. So that's x. So that's just x equals 3. Yeah. Or the answer to the simplified version of the original expression is 3. Morning, Jason and Elizabeth. Glad you're here. So notice that what we're saying here is that this base raised to what power is equal to 8? So similarly, 5 raised to what power is equal to 125? 5 to the third power is 125. So I could have rewritten that. 5, well, to the third is equal to 125 once we know that it equals 3. Here, 1/2 to what power is equal to 1/8? Well, no matter what we raise 1 to, it's going to equal 1. And 2 to the third power is 8. So that means that this has to equal 3. 1 to what power is 1? That's what this is saying. 1 to what power is equal to 1? Any power we want. All real numbers. And 17, this log base 17 of 1, 17.5 of 1. So what does 17.5 have to be raised to equal 1? 0. And you can probably see that all these are related to each other right here. Questions on that warm-up? How do the expressions on the left relate to the expressions on the right? How would you describe that relationship? How does this relationship relate to that relationship? Anybody? Good Monday morning. It is hard to get rolling on a Monday morning at 9, well, 23 now. What do you think? How do those relations relate to each other? Right, right. Yeah, good. Thanks, Alina. Yeah. So here we figured out what power will raise our base to equal what we are taking the log of there. So they're kind of like undoing each other, aren't they? They're kind of the opposites. So we have one that's a log and one that's an exponential. How would you explain how to calculate a logarithmic expression to a middle school student? So, thinking about this, how would you explain? Let's assume that a middle school student knows about exponentials. How would you explain to them how to calculate a logarithm? Take a moment and think about it. And when you're ready and feeling brave, turn on your mic and start talking. I'm going to take a moment and fill my coffee up while you guys think. How would you explain how to calculate a logarithm to a middle school student? Anybody? Well, yeah. Hmm. Jacob, that is so good. Yeah. So, for instance, on this first one, log base 2 of 8, Jacob says, and I'm going to use mathematical terms that you didn't use, Jacob, but that you explained. How many times do I have to multiply the base to get the argument of the logarithm? But you know what, Jacob? Yours was probably better for the middle school student because you said, how many times do I have to multiply this small number by itself to get this big number here? I like it. Yeah, let's just say that. How many times do you need to multiply the small number? And here I'm going to insert base in parentheses by itself to get the big number. The argument. Jacob, thank you for speaking up there. Awesome. We all benefited from your thoughts. Appreciate it. So far we've talked about inverse operations. We've talked about inverse operations, for quite a while in math. And so what does an inverse operation do? Can someone give me an example of inverse operations? And then maybe two, and then we can talk about what inverse operations do. What's the inverse operation of addition? Yeah, subtraction. So addition and subtraction are inverse operations. What's the inverse operation of multiplication? Thank you. Multiplication and division are inverse operations. And then we have roots and powers are also inverse operations. So what do inverse operations do? Can someone tell me more generally what they do? We use this language when we're solving an equation. They undo each other. They undo each other. So I'll give it a little example here. So if we had x plus 3 equals 7, and I know this is super easy. You see it's 4. So we're adding 3 to our unknown value x. So to undo this operation of addition, we use subtraction, because we make a 0 right there. They undo each other. Okay, so we have x equals 4. So that's what I mean by undoing each other, right? Does anyone have an idea what inverse functions might do? There are such things as inverse functions. Of course they are, because when we have a concept, it's nice to be able to stretch that concept and use it in new ways. When I say inverse operations undo each other, and then I ask you, what about inverse functions? What do they do? You should say, hey, let's just copy that, paste it down there. I don't know what it means, but hey, they undo each other. That's right, they do undo each other. Right? So a function, so when we talk about functions, we're talking about, like function notation, f of x. So something like f of x is equal to 2x plus 3. So this is a linear function, and it's written in slope-intercept form. It's written in function notation form. A function is a map. What does a map do? It tells you where to go. A function is a map from one set of values called the domain to another set of values called the range, such that each value in the domain is mapped to a unique value in the range. That sounds so technical. So in other words, a function takes a number x and spits out a number y. Using that definition, what does an inverse do? Well, if it undoes a function, then it takes a number y and spits out a number x. An inverse function takes a number y and spits out a number x. So here's our function f. It takes this value a. These are numbers over here, and numbers they're all numbers. It's just written as letters. It takes in this number a. It can be actually a letter too. It doesn't really matter, and spits out the number 3. F takes in b and spits out 1. F takes c and spits out 2. Now, this couldn't be a function if A spit out 3 and A also spit out 1, if it spit out both of those, that wouldn't be a function, okay? It can only spit out one thing for each input. Now, it could be the case that A spits out 3 and B also spits out 3. That's okay. That's all right. Okay. But so we have this function that takes the domain, and everything in the domain goes to one thing in the range. The inverse function, f inverse, so the way we write it is like a little exponent to the -1 power, but it's not an exponent, okay? That's just what it looks like. So this is called f inverse. It's the inverse function to f. So because f takes a to 3, f inverse takes 3 to a. Because f takes b to 1, f inverse takes 1 to b. Because f takes c to 3, or 2, excuse me, f inverse takes 2 to c. Notice that it just basically sends the output back, or sends the input back. So here's the input. It sends it over here to 3. The inverse takes that input and sends it back to the original input. All right. Here's an example of tables. And we're using this function f of x is equal to 3x plus 1. So when you plug -2 in here, so you have, just to make sure we're all on the same page here, when we plug in -2 to f, well, let's see, you get a 3 times -2 plus 1 is -6 plus 1 is -5. So that's why when the input is -2, the output is -5. And then we can see that the rest of that is just following the same pattern. As we increase our x value by 1, we increase our y value by 3. And that's how we can see that our slope is 3. Okay. So the inverse function of f, takes -5 and spits out -2, because the original function takes in -2 and spits out 5. So notice that all we've done is we've taken all of the input and switched them to output, and we've taken all of the output and switched them to the input. However, they still line up with each other. The input and the output stay together in f and its inverse. How would you describe this if you were going to describe it? And that will answer our question here. What do you notice about the two tables? Each time you're brave in class and speak up, it builds your character. Think about, there you go, Sam. Let's hear it. Oh, interesting, Sam. We will talk about, I like where you're going with this, thinking about how they're going to look when we graph them. When you say they are opposites, I think what you're saying is that the input and output are switched. Great. I'm just going to be explicit about that. And I don't know if I can fit it. I squeezed it in there. That reminds me, my son he's about 3/4 of the way through writing 100 words. It was an assignment that he got last Friday. And this is it's kind of hard to read. He's in kindergarten, so the lines are a little small for him, and it's good practice for him. But yeah, most of his writing looks about like that right there. So good stuff. All right. So Sam, you asked for it. Here it is. Is the red, you don't have to answer this, Sam, but is the red or the blue graph 3x plus 1? F of x is equal to 3x plus 1. Anybody? Oh, good. The red one is f of x is equal to 3x plus 1. Yeah, Sam, thank you. The end of my coffee here is sludge. Woo! And so the blue line is the inverse of f. What do you notice about the two graphs? Do you notice anything? If you didn't have the blue one here, it was gone. And someone said, hey, we have this function f, it's f of x is equal to 3x plus 1. How do you know where its inverse will be? Hey, Vincent, glad you're back. Does anyone see the relationship between the original function f and its inverse, f inverse here? Might be kind of hard to see. So it's really cool. What happens is that they are reflections of each other across this line y equals x. So this is the line y equals x. And the original equation, if we reflected it across that line, we would get its inverse. So they are reflections. And if you haven't heard the Talib Kweli album, Reflections Eternal, oh man, I really suggest going back and listening to that one. Does anyone even know who Talib Kweli is? No. Most Def? No. Crickets. All right. Well then, I'm old. That's true. Here we go. All right. So, um, here's another one. So, again, we have our original function g of x is equal to 3 times the quantity x plus 1 squared. Oh, what kind of a function is that going to be? What, what kind of function or what kind of graph will it make? It is a quadratic function because it's raised, our power is raised to the second. Excuse me, our variable x is raised to the second power. It's a quadratic and it will create a parabola. So, for instance, look here, we have a -2 maps onto 3, and 0 also maps onto 3. Since -2 is 1 unit away from -1, and -1 is 1 unit away from 0, since these values are the same, this is our vertex. All right, cool. So again, we can notice here that they are, the input and the output are switched. So we can say the domain and the range are switched. I'm not gonna, well, I want to, well, actually this should be g of x, g inverse of x, but I want to flag this for a moment. Does anyone know why I'm flagging g inverse of x here? And it has to do with this right here. This is not a function. So writing it in function notation is actually kind of sloppy math. Okay? Sloppy math. I want you to be aware of it. We do this sometimes, but it's not great. All right? But we wanted to get a point across here of we can find the inverse of a function. And sometimes the inverse of a function is not a function. So here we have our original function. We found its inverse, and it's not a function. That's okay. And we can see here that we have our original function, g of x. Notice that this is plus 0. So our h is -1 and our k is 0. So our h is -1 and our k is 0. Taking you back a little bit there, probably. And what I want you to notice is that, again, g inverse, this is sloppy math. This thing is not a function. But you can see that if we reflect across the line y equals x, we get the graph over here. So if we take this original graph, we reflect it across the orange line there, we will get this graph over here. And it's because this one is symmetric across a vertical line, its inverse must be symmetric across a horizontal line. You know what? I think this is not correct. I think that it should be down here like this. I'm sorry about this. This is not, I'm not pleased with this, but this stuff happens. All right. So here, I don't want to use that color. I'm just going to use black here. So there, and this is, yeah, okay. All right. All right. So the graph, its inverse should look like this. I'm really sorry about this. The graph has two colors because you only get each half when you find its inverse. So we'll talk more about that later. All right. So an inverse function undoes or inverts the original function. In other words, if f maps a number x to a number y, the inverse f inverse maps the number y to the number x. In other words, If xy is a point on the graph of f, then the point yx is on the graph of f inverse. In other words, the inverse function flips the x and y values of the original function. So I want to show you how I knew that something was going wrong here. So I found this point right here, negative 1, 0, right? So that means that the point right here, 0, negative 1, has to be on the graph, because you take the x part and move it into the y position, and the y part and move it into the x position. And that is how we can invert a single point. And really, when we take this graph and invert every single point on it, we get this graph. So here we have, here, let's just do it in, I'll do, whoops, kind of this pink color. So here we have the point negative 2, positive 3. That means that the point 3, negative 2 has to be on the graph, because we take the x part, we move it into the y position, we take the y part, we move it into the x position. So that is how we take this point and invert it into that point. Questions? All right. So the line of reflection is the line y equals x. And I'm going to put it in this purple here. And have you guys ever been trying to solve a problem? Maybe a math problem, maybe not a math problem. And you were working on it, and you were working on it, and you stepped away from the problem. You were frustrated, you stepped away from it, and then it sort of hit you later, and you figured out the answer to your problem. Anyone ever had that experience? Or is it just me? Just me. Okay. Well, what I'm going to say is I'm going to take a quick break here. We're going to get up, we're going to move our bodies. So I'm going to pause the video. All right, so coming back together, the question I posed was, why does it make sense that the line y equals x is the line of reflection for a function and its inverse? Can anyone answer that or try? Well, here's the way I see it. If we have some function f that takes the point x and outputs the point y, then f inverse has to take the point y and output the point x. So x must equal y, and y must equal x when we think about just a function and its inverse. So the line y equals x is the line that reflects one across to the other. Putting this in words is kind of hard for me to do, and I've never really seen a teacher explain it this way, but it's the way that I see it, and I hope that it makes sense to you. Is there anyone who can say what I'm saying in their own words, or is willing to give it a shot? Okay, that's fair. All right, domain and range. I want to, I wish that this example didn't show up here multiple times, but it is. So I'm just gonna keep on fixing it, and we're gonna bear with it. So if we think about the original function, what is the domain of the original function? What are the possible x values for the original function? Let's call this f. So for f, what x values are possible? Well, all of them. If we go out that direction forever, all of the x values can be input. And if we go out to the right that way forever, all of the output, or all of the f values are possible output. So the domain, we can write it this way, from negative infinity up to positive infinity. And the range, well, the range is not from negative infinity to positive infinity. The range, you can only start here where y is 0 and then go up. So the range is such that 0 is less than or equal to y. So y, you could also say y is greater than or equal to 0. It's a perfectly good way of saying it as well. Now, when we think of the other graph down here, this graph, it's not a function, but it's the inverse of the original function. Well, down there, and again, it's sloppy math, so I want you to be aware that I'm this is kind of sloppy math. F inverse, we're calling it the inverse. The domain, well, what x values are possible? Well, we can only have x values that are to the right of that. So x has to be 0 is less than or equal to x. We could also say x is greater than or equal to 0. And the range, well, we can go up that way forever and down that way forever. So that goes from negative infinity, negative infinity up to positive infinity. And so what I want you to notice is that when we think about some function and its domain and its range, that its inverse just flips the domain and the range, which makes sense. Because really that's all we're ever doing is switching the x and the y. All right? Questions here? No questions.